Still working in section 5.3, let's look at example 7. This is kind of one of these leading questions, and this kind of process will come in much later on in the class. What we want to do in example 7 is find the z-scores for which 99% of the distribution's area would lie between the negative of that z and the positive of that z. So especially with something like this, it's a good idea to try and draw a rough sketch of the graph. Draw something like this, and here's our 0 because it's a z-score. So we have a negative z over here to the left, a positive z over here to the right, and 99% or 0.99 of the area is going to be between those two z-scores. We want to find their values. Again, realistically, for a problem like this, because it's a z-score, it's symmetric, you only really need to find one of the two values because they're just going to be opposites of each other. Let's, in particular, focus on finding this particular z-score. Here, let's look for the lower one. Let's see if we can find this one right here. Again, if you want to find a z-score, given a area, percentage, or probability, then we're going to be using that inverse norm function again. And the thing to always keep in mind is if you want to find that z-score from an area, then in particular what you need to have is the cumulative area, which means I need to figure out how much area is over here to the left of that negative z. Well, we weren't given that. What we were given is that it's 99% or 0.99 between those two. So given that information, how can we find the amount of area in this left tail, this cumulative area over here? Well, one thing that we do know is that the total area under the curve, all of it would be equal to 1. And if I took 1 and subtracted the middle area, then what would be left would be the area not just in one, but actually in both of the two tails. So if I do 1 minus the middle, that'd be 0.01 or 1%, then I have the amount in the two tails. And because it's symmetric, if I just take half of that, that would tell me exactly how much would be in the left tail. Half of 1% would be half of a percent, or 0.005. So the cumulative area to the left of this z is 0.005, and now that'll allow me to use the inverse normal function. I go second, distribution, go down to choice 3, inverse norm. Area to the left is 0.005. We're still dealing with z-scores, so it's a standard normal 0 and 1. Go ahead and hit paste, hit enter, and to 2 decimal places we would get a z-score of negative 2.58. Negative 2.58. So that would be the lower of the two z-scores, and then conversely the positive one would be a positive 2.58. So what we would know is that 99% of the standard normal distribution lies between z-scores of negative 2.58 and positive 2.58. In the remaining examples in this section, what we're now going to do is kind of open it up, and instead of focusing necessarily on the standard normal, we're going to look at any general normal distribution that can have a different mean and standard deviation, different than the 0 and 1 we've been working with. For example, in question 8, they say that a survey of men in the US aged 20 to 29 have a mean height of 69.9 inches and a standard deviation of 3.0 inches. So again, whenever you read a problem like this and you pick up on that specific value of a mean and standard deviation, it's a good idea to write that somewhere off to the side. So the mean, mu, is 69.9. The standard deviation, sigma, is 3.0. The first question is, what height represents the 90th percentile? So we're looking for the value, this would be an x-score by the way, such that 90% of the values would lie below this particular height. Well, if this person's going to be in the 90th percentile, certainly they're going to be taller than normal, so their value should be somewhere over here to the right of the mean, and the proportion that's going to lie to the left is going to be that 0.90 for 90%. We can again find this value using the inverse normal function because I have an area or a probability and I'm looking for a x-score or z-score. That's when you use inverse normal. We do second distribution. we're going to go down to inverse norm. For the 90th percentile, the area to the left, the cumulative area is 0.90. This distribution has a mean of 69.9 and a standard deviation of 3. Go ahead and hit paste. We hit enter, and we'll round this one to 2 decimal spots. It'll round to 73.74. So any man that would have a height of 73.74 would put them in the 90th percentile. So 90% of the individuals would have a height that is less than 73.74 inches. We can do a similar question. We can find the height that represents the first quartile. Recall that the definition of the first quartile is a value such that 25% or 0.25 of the values would lie below that number. Because it's not quite a full half, this first quartile should lie somewhere to the left of the mean, so that the cumulative area to the left of it can be the 0.25. We again do second distribution, inverse normal. Cumulative area this time is going to be 0.25. The mean is 69.9. The standard deviation is 3. Go ahead and hit enter. Again, for those of you following along using a TI-83, remember when you go to that distribution menu and you hit enter on the inverse norm, it puts that command on your home screen. You have to remember to put those 3 inputs in that correct order. It's cumulative area to the left, comma mean, comma standard deviation. Go ahead and hit enter, and we would get to 2 decimal places a height of about 67.88. So the first quartile for the heights of these men, meaning that 25% of them would have a height that's less than 67.88 inches. Let's look at a different normal distribution. This time we're looking at the annual consumption per capita in pounds of oranges in the US. They say that it's approximately normally distributed with a mean of 9.9 and a standard deviation of 2.5 pounds. So here our mu is 9.9 and our sigma would be 2.5. The first question asks, what is the smallest annual per capita consumption of oranges that would put somebody in the top 10%? Okay. So what amount of oranges would you have to eat in order to be in the top 10%? So we have a normal distribution. Can kind of go ahead and draw our bell here. Our mean is 9.9, so that's where our average would be. Certainly if somebody's in the top 10%, they're going to be well above average. So this value we're looking for is going to be somewhere over here to the right. And if it's the top 10%, then that means that the proportion of the probability above it would be 0.10. If I want to find that value, that unknown value to us, then I don't want to know the area to the right of it. I need to know the cumulative area, which would be the area to the left. If it's 0.10 above, then I can do 1 minus 0.10, which would give me 0.90 would be the proportion of the area below it. So the cumulative area this time is going to be 0.90, and that's what I'm going to have to use in the inverse normal function. Makes sense, right? If it's the top 10%, that value is going to separate the top 10% conversely from the bottom 90%. Second vars, to get to our distributions, inverse norm. We just said that the cumulative area is going to be 0.90. For this data set, the mean was 9.9, and the standard deviation was 2.5. Go ahead and hit enter, and enter again, and we would get to, let's say, 2 decimal places, 13.10. So any individual that consumes 13.10 pounds of oranges would be in the top 10% of all consumption. The last part of this says, what is the largest annual consumption of oranges that would place somebody in the bottom 5%? You can kind of go ahead and draw it out. So here's our bell-shaped curve. We're looking for the bottom 5%. That's going to be 0.05. That would not be a whole lot of area to the left, which means that this value should be one that's going to be below the mean or be below average. You do second distribution, inverse norm. It's already going to be the bottom 5%, so 0.05 would be the cumulative area to the left. The mean was 9.9, standard deviation was 2.5. Go ahead and hit enter, and we would get a consumption of 5.79. So anybody that consumes 5.79 pounds of oranges would put them in the bottom, or less for that matter, would be in the bottom 5% of all orange consumption. We'll do one more example, kind of closely related. They didn't copy this down in the notes that I handed out or put on D2L, but if you look at this problem, the mean as stated in the book was 20.7, and its standard deviation is going to be 4.2, and now we're looking at the annual consumption of ice cream in pounds. The question they ask first is, what is the largest annual consumption per capita that can place somebody in the bottom 10% of consumption? So we can go ahead, it's a good idea to draw a rough sketch. Here's our normal distribution. The mean would have been quoted to us as 20.7, that should have been on there. And we want to be in the bottom 10%, so we're going to be somewhere over here to the left. We want to find that X score. To find that X score, we can use the inverse norm. Second distribution. Go down to inverse norm. The bottom 10% would have a cumulative area of 0.10. The mean is 20.7. The standard deviation would be 4.2. Go ahead and hit paste, hit enter, and we would get about 15.32. So 15.32 pounds would separate the bottom 10% of all ice cream consumption. We have one more. It says, between what two values does the middle 80% of consumption lie? This is awfully similar to one we did a little bit ago with a z-score. So I have some value that would be below the mean, some value that would be above the mean, such that 80% of the distribution should be between those two values. Now, the one thing that will be a little bit different, unlike the z-score where we knew that they were going to be opposites of each other, is because we have a mean of 20.7, that's no longer going to be the case. We really do kind of need to find each one on their own individually here. Let's again start by finding the bottom number here. So for this lower bound, we know that it's 80% between, but I need the cumulative area to the left. So we're going to use the same process that we used before. If I do 1 minus 80%, or maybe 100 minus 80%, that would tell us that it's going to be 20% total in the two tails. Because it's symmetric, if I take half of that, I get the area in one tail, which would be 10%, or 0.10 would be this cumulative area. Therefore, I can find this consumption by using inverse norm, cumulative area, which is 0.10, mean, and standard deviation. So we do second distribution, inverse norm, a cumulative area of 0.10. The mean was 20.7. Standard deviation was 4.2. Go ahead and hit enter, and we would get 15.32. Let's now go ahead and see if we can find this one right here. We want to find this particular upper bound. Well, we know that it's 80% between these two, and it's an additional 10% below the first one. So the total area, the cumulative area to the left of this guy here, should be 10% plus 80%, which is 90% or 0.90. So it's going to be second distribution, inverse norm, 0.90, mean of 20.7, standard deviation of 4.2. Go ahead and hit paste, and we would get 26.08. So consumption levels between 15.32 pounds and 26.08 pounds of ice cream would comprise the middle 80% of all consumption levels. So even though for one like this, you couldn't necessarily do like what we did when it was a z-score with symmetric interval, you said, okay, one's going to be a negative, then it'll be positive. One thing that will be true, however, is you can't just like change the sign, but their distances respectively to the middle should be the same. If you computed the difference between 20.7 and 15.32, that length would be the same as the difference between the 26.08 and the mean, which would be 20.7. So you could essentially find that distance between these two, add it to the 20.7 as an alternative to doing a separate inverse normal calculation. However, I think this is a good way to do it though, because it really reinforces the methods we learned in this particular chapter.